Om Sri Sai Ram. My humble salutations to my beloved Bhagwan, respected elders, and my dear students. Hearty welcome to number theory class. Today we are going to learn unit number 5, quadratic residues. So, theorem number 1, Euler's criterion for quadratic residues mod P. Now, the statement of this theorem is that let P be an odd prime and GCD of A and P equal to 1. Then A is a quadratic residue of P if and only if A to the power of P minus 1 by 2 is congruent to 1 mod P. That means there are two statements. One is that A is a P is an odd prime and GCD of AP is equal to 1. So the statement says that if A is a quadratic residue, then A to the power of P minus 1 by 2 is congruent to 1 mod P. On the other hand, if A to the power of P minus 1 by 2 is congruent to 1 mod P, then A is a quadratic residue of P. Now, before proving this theorem, let us consider an example. Suppose P is an odd prime, let us say 13 and A equal to 2. Then a to the power of p minus 1 by 2, that becomes 2 to the power of 13 minus 1 by 2, that is equal to 2 power 6, which is equal to 64. When you divide 64 by 13, the remainder is going to be 12. Therefore, 2 to the power of 13 minus 1 by 2 is congruent to 12 mod 12 congruent and 12, which is nothing but minus 1, congruent to minus 1 mod 13. So it is not satisfying the condition that a to the power of p minus 1 by 2 is congruent to 1 mod 13. So a is equal to 2 is not a quadratic residue. On the other hand, if p is equal to 13 only and a is equal to 3, then 3 to the power of 13 minus 1 by 2 equal to 3 power 6. 3 power 6 can be written as 3 cube into 3 cube, that is 3 cube whole square. 3 cube means 27 whole square, and when you divide 27 by 13 we will get that is equal to uh, 1 whole square, that is nothing but 1. Therefore 3 is a quadratic residue of 13. Now we are going to prove the theorem. Now the condition is necessary condition. So we are going to assume the left hand side and we are going to prove the right hand side. What is there on the left hand side? We will assume that A is a quadratic residue of P, where P is an odd prime number. Now, when do you say that A is a quadratic residue of P? By the definition of the x square is congruent to A mod P has a solution. So let us say x1 is a solution. Therefore, x1 square is congruent to A mod P. So now what is that we have to prove? We are going to prove that A to the power of P minus 1 by 2 is congruent to 1 mod P. Since the GCD of A and P equal to 1, we see that GCD of x1 and A is also equal to 1. Suppose if it is not so, that means GCD of x1 and P is not equal to 1, then that implies that P divides x1. That implies in turn x1 is equal to, that is congruent to 0 mod p. Therefore, x1 square is congruent to 0 mod p. From 1, a is congruent to 0 mod p. That implies p divides a, which is a contradiction to the fact that GCD of a and p equal to 1. By Fermat's theorem, if as x1 and p, the GCD equal to 1, we have x1 to the power of p minus 1 is congruent to 1 mod p by Fermat's law. Now multiply and divide the power by 2, we get x square whole to the power of p minus 1 by 2 is congruent to 1 mod p. In particular, if you consider a is equal to x1 square, then a to the power of p minus 1 by 2 is congruent to 1 mod p. So the sufficient condition. Conversely, let us assume that a to the power of p minus 1 by 2 is congruent to 1 mod p, that holds. Now we have to prove that A is a quadratic residue of P. That means we have to find that x square is congruent to 1, x square is congruent to A mod P as a solution. So let us say that R be a primitive root of P, then R power K is congruent to A mod P for some K belongs to Z. where 1 is less than or equal to k less than or equal to p minus 1. Now take the power of p minus 1 by 2 on both sides. Therefore, r power k whole to the power of p minus 1 by 2 is congruent to a to the power of p minus 1 by 2, which in turn is equal to 1 mod p. That implies automatically r power k whole power p minus 1 by 2 is congruent to 1 mod p. Therefore, here what is the concept that we are using, that if the order of a mod p is equal to m, that means a power m is congruent to mod n, where m is the least positive integer, and a power k is also congruent to 1 mod n, then automatically m divides k, because m is the least positive integer, which fulfills the condition that a power m is congruent to 1. So we have r power k whole to the power of p minus 1 by 2 congruent to 1 mod p, and r is a primitive root of p. Therefore, r to the power of phi of p is congruent to 1 mod p. Then phi of p divides k times p minus 1 by 2. That implies k times p minus 1 by 2 is equal to phi of p 1 to 1. So we are having k times p minus 1 by 2 is equal to p minus 1. In other words, k by 2 equal to L, that implies k equal to 2L. So r power k is congruent to a mod p implies r power 2L is also congruent to a mod p. Now that implies r power k whole square is congruent to a mod. Okay, so x square is congruent to a mod p implies r to the power of 2L is congruent to a mod p. It implies r to the power of L whole square is congruent to a mod p. Therefore, for x is equal to x power r power L, the above congruence holds. Therefore, A is a quadratic residue of P. I hope this is clear. Okay, thank you.